Okay, so this is additional note 2 at 3. So during the lecture 2, I left some loose ends, a couple of topics, and I promised to discuss that separately, and that's what I'm going to do that now. So the two topics are number 1, distribution laws involving derivative of Dirac delta function. So distribution laws involving derivative of Dirac delta function, and the second topic is functional derivatives. Now, in the first case, in the first topic, we have to prove an identity which was used in the lecture, which is as follows: derivative t of delta t minus t prime o hat t prime is equal to derivative delta t minus t prime o hat t plus delta t minus t prime del t of o hat t. That's equation 1. So before I go on to discuss how to prove this identity, let me make some general comments about what distributions are. So delta function is a distribution. Dirac delta function is a distribution. Let me make some general comments about what these objects are. So the general comments. So usually we deal with ordinary functions. Ordinary function is a map from one space to another. For example, if you have a real function in one real variable, then fx is a map from R to itself. It could be R to C, a complex, if it's a complex function, or any more complicated space. Both the domain and the target can be more complicated than simple real line, and that is what a function is. Now, knowing this map, what we can do is to calculate all possible integrals involving this function, if it is an integrable function. So, knowing this enables us to calculate all possible integrals of this form, integral dx fx times phi x, and such enough for a given x, we can choose arbitrary phi, which are all smooth functions. And let me define that to be an inner product between f and phi. It's like an inner product, and you can view this as the inner product. We are familiar with this terminology from the vector analysis. For example, we know that we can calculate inner product between two vectors. So if you know, you can view this, you can interpret this equation in the following manner. If you know the inner product of a specific vector with an arbitrary vector, which you can vary, you can change that the test vector and calculate the inner product. And if you know the results of all possible such inner products, then you basically know what that vector is. That is one way of describing that vector. So you could view it that way. So if you know for an arbitrary function phi, so this is a test function which we take to be smooth, or C infinitely differentiable function. If you so if you take all possible such functions, and since this result can be calculated, since this integral can be calculated, because I know what fx is, and that gives us the entire data of all possible inner product between the fixed function and all possible test functions. So that is equivalent to knowing the function itself. So this is more complicated way of, in a sense, describing a function. Let me call this, which we are familiar with, as A, and this is B. So A and B are two different ways of describing a function. Now, if you know the function, if there's a description in the A form, that means you know the function as a map from R to R, then you automatically know what B is. You can describe B, but it turns out that if you know B, then that doesn't necessarily imply a description like A exists. This is, in some sense, you could also view this as this result as if as a function of phi. So because for phi, as if phi is an argument, it's a test function. You are varying this test function. You are calculating this inner product for all possible values of phi. That's like an argument. For each such argument, you are calculating f. So this B also allows you to view f as a function over the space of test functions. So all possible test functions, we are now familiar with viewing a function as a point in a space. So I'm talking about that space for phi x. So phi x is a function, but the space of phi x is an infinite dimensional space where phi of x sits as a point, and as if you are calculating f at that point. You can interpret that way. So this allows you to look at f as a function in the space of all possible smooth test functions as well. Now, as I just said, that A implies B, but not the other way, not necessarily the other way. So distribution or a generalized function is of that kind. So distribution or a generalized function is something for which B exists but not A. There is no A type of description, and that's what a Dirac delta function is. So example is Dirac delta function for which the result is given by dx fx delta, sorry. So your fx is the Dirac delta function and phi x, and the result is by definition by assertion is phi of 0. Okay, so and you also have other statements like, so dx derivative of delta x times phi of x must be 0, because this is the total derivative, and the result this result takes you to the boundary of x of real line. Suppose you are integrating over maybe a segment, say a to b, which includes x equal to 0, where delta function is supported. So delta function is non-zero, gives non-zero result only if you include x equal to 0 point in the integration. That is implicit in my writing here. So is here. It is a to b, which includes the x equal to 0 point, and this total derivative takes you to the boundary, and that result will be will involve delta a delta calculated at the boundary values, and since delta is supported only at x equal to 0, the result is 0. So this way, you can calculate integrals of expression which involve delta x. Now, derivatives of and therefore delta x is a distribution. Now, derivatives of delta x are also distributions. And therefore, such distributional identities need to be verified by multiplying with arbitrary test functions and subsequently integrating. So identities must be verified by first multiplying with arbitrary test functions and then integrating over the relevant range. So that is how we should look at this this identity. We should multiply both sides by an arbitrary test function and then integrate. Now, there is one difference here. There are two differences here. One is that this involves an operator, so O hat. We shall now first forget about that. We shall just verify this identity for classical functions, which are not operators, and then at least I will write down the statements that need to be proved for classical functions, and then for how to use that for the operators will be the next thing to discuss. And there is one more thing, is that there are 2 points involved here. So, and the derivative is acting on one of the t's. Other t has no derivative, but here the time derivative acts on delta function but multiplies with an operator t prime, and this expression is being written in terms of terms where the operator sits at t. That is the difference on the two sides. Therefore, since there are 2 points involved, one could multiply an arbitrary test function and the at 2 points, and also integrate over 2 t's, t and t prime, and therefore giving rise to total 4 conditions. So identity one implies that the following 4 conditions should be right. Integral dt LHS phi at t is equal to integral dt RHS phi at t, integral dt prime LHS phi at t, integral dt prime RHS phi at t. where of course LHS and RHS are nothing but these expressions. This is your LHS and this is RHS. I'm just using a simple, I'm using it some cryptic notation here, but it is easy to understand. You know what I mean. And the two other identities where you change phi t to phi t prime, and so that will be integral dt LHS phi t prime is equal to integral dt RHS phi t prime integral dt prime LHS phi t prime is equal to integral dt prime RHS phi t prime. So these are the four, this is a set of four equations that one needs to verify in order to verify this identity, identity one. Now let me make comment about how to go to operator version of that. That is nothing but so your operator has an argument t, which is a classical number. It's a parameter that parameterizes the operator. That's what this is. So so you can lift that test function also to an operator, an arbitrary operator with some desired properties. So all possible operators with right kind of properties that are acting on the Hilbert space. So your LHS is an operator, RHS is an operator. Multiply with phi hat of t, and then take expectation value. So it will mean like integral dt LHS operator. LHS operator means nothing but this. This is of course classical, but this is an operator. Multiplying phi hat of t is equal to integral dt RHS operator phi hat t. So you can view it this way. So this is operator version of that, and so on for all the other. So let me verify one of these four equations. Let me choose this one, the third one, to verify. Now, so dt LHS is derivative delta t minus t prime o t prime. I have to calculate this. This is since the entire, see, this time derivative is a total time derivative because all the other, so this acts on this time, but all the other dependencies on t prime. So it's a total time derivative, and therefore after integration it will take you to the boundaries, and at the boundary delta function will not have its support, so this must be 0. So it is integral del t delta t minus t prime o t prime, and it is 0. Similarly, on the right hand side you have integral del t integral dt del t minus t prime o t plus delta t minus t prime del t of o t phi t prime. So for the first term, we have to show that this is 0. For the first term is nothing but it's a total derivative of both the terms minus delta times derivative of OT. So this is dt minus delta t minus t prime del t of OT plus delta t minus t prime del t. You can do that because you are you can do this, you can write from here to here, because what you are doing is that you are writing this as a derivative with respect to t of the entire thing, like this term times this term, 3 terms. But it is only this term minus all the derivatives that you have done, that you have written extra, which is derivative here, acting here, and here, but this term is t prime, so it doesn't act act on it gives 0, and therefore you have only one term. So that is it. Now this result is 0 because these two terms cancel. So so this is how you prove the third identity, and similarly it's straightforward to prove all the other identities. Okay, now I shall move to discussing the functional derivatives.